Hey everyone. So, you see those big headline statistics all the time, right? The national average for this, the unemployment rate for that. But honestly, the really interesting stuff often happens when we zoom in, when we look at specific groups within that larger population. That's exactly what we're talking about today. Estimation in domains. It's a super powerful way to get a much clearer, more detailed picture of what's actually going on.
But think about it for a second. When a pollster does a big national survey, they're taking a random sample. They don't go out looking for exactly 100 boat owners or 50 recent college grads. They just sample randomly. So how in the world can they turn around and give us a confident estimate for just the boat owners? What happens if one random sample gives them 50 boat owners and the next one gives them 75? That right there, that's the big statistical puzzle we're going to unpack.
Okay, so here's the plan. First, we'll talk about why we need to look past that one big grand average. Then we'll get into the main challenge, what I like to call the sample size surprise. After that, we'll break down the really clever statistical fix that makes this all work. From there, we'll see how to go from calculating averages to estimating totals, and we'll wrap it all up by talking about why this focus on subgroups is so important in the first place.
All right, let's jump in. First things first, we've got to get past the idea that one single number can tell the whole story for an entire population. The real magic, the real insights, are almost always hiding in the pieces that make up that whole.
And in statistics, the word we use for these specific groups is a domain. A domain is really just any subpopulation that you, the researcher, are interested in. It could be something demographic, like men versus women. It could be geographic, like all the Western states. Or it could even be based on some characteristic, like whether or not someone owns a big motorboat. The whole point is to define these groups so we can drill down and get more specific numbers. So this leads us right into the heart of the problem, the sample size surprise. And this is what really separates domain estimation from the kind of stuff you might have learned in your first stats class.
Imagine we take a simple random sample of 1,000 people to estimate, say, average income. That's all well and good. But what if we also want to know the average income just for women? Well, because the sample is random, we have absolutely no idea beforehand how many women we're going to get. It could be 480, it could be 510, it could be 535. We can't force it to be a specific number.
And this, for us as statisticians, is the core of the issue. The sample size for our domain, which we'll call n sub d, is itself a random variable. It's not a fixed number we decide on. It's a result of chance. And that's a huge deal, because all those standard formulas we know, like s squared over n for the variance, they all assume n is a fixed, known constant. When our denominator n sub d is random, that assumption goes out the window, and we need a totally different way to figure out our uncertainty.
So what do? Well, this is where it gets really cool. Statisticians came up with a super elegant solution. Instead of trying to fight against the randomness of n sub d, they found a way to build it right into the math. It's just a beautiful example of reframing a problem to solve it.
And that elegant solution is to treat the whole problem as a special case of something called ratio estimation. The big idea is to write the number we want, the domain mean, as a ratio of two other numbers. We then use our sample to estimate that ratio. It's a mathematical workaround that lets us properly account for the randomness of our domain sample size.
Let's walk through exactly how this trick works. Step 1. For every single person in our big sample, we create an indicator variable. Let's call it xi. If the person is in our domain, xi is 1. If not, it's 0. Simple. Step 2. We create a second variable, ui. If the person is in our domain, ui is just their value, their income, or whatever we're measuring. If they're not in the domain, ui is 0. And now for step 3, the magic. If you take the total of all the ui's and divide it by the total of all the xi's, what do you get? Well, the sum of the x's is just a count of how many people are in the domain, our random n sub d, and the sum of the u's is the sum of the values for only those people, so the ratio is the domain total divided by the domain count, which is, by definition, the domain mean. We've turned it into a ratio estimator.
Now, because we set this up as a ratio estimator, we have to use the proper formula to calculate its variance. And yeah, what you're looking at here is the standard, full-blown Taylor series approximation for the variance of a ratio. It looks a little intimidating, I know. You've got the sample variances of our u and x variables, and also the sample covariance between them. But what this formula is doing is correctly capturing the variability of both the numerator and the denominator of our ratio and how they move together. It's the right way to calculate our uncertainty.
But here's the great news. As long as our sample is big enough,
That scary formula simplifies to something much, much more intuitive. Let's break this one down. You've got the finite population correction, that's standard. But look at the main part, s squared sub yd divided by n sub d. That s squared sub yd is just the sample variance of our variable, but calculated only using the folks who fell into our domain. So what this tells us is that the standard error for our domain mean basically acts just like the standard error for a regular mean from a simple random sample of size n sub d taken right from that domain. The whole ratio estimation framework is the rigorous proof that lets us arrive at this beautiful, simple result.
Okay, so we've got a solid handle on estimating averages for subgroups. But what about totals? What if we don't want the average farm acreage in the West, but the total farm acreage in the West? Let's see how we can extend these ideas to do that.
So when you're estimating totals, it really comes down to two different situations. Scenario 1 is the easy one. If you happen to know the true population size of your domain, let's call it big N sub d, maybe from census data, then your best estimate for the total is just that known size, N sub d, times your estimated domain mean. Simple. But more often you're in scenario 2. You don't know the domain size. In that case, you have to do something different. You take the total population size, big N, and multiply it by the overall sample mean of that special U variable we created. Remember, U is the value if you're in the domain and 0 otherwise. So by doing this, we get a solid estimate of the domain's total contribution to the whole population.
Let's make this real with an example from the Census of Agriculture. So a simple random sample of 300 counties was taken, and we can split them into two domains, counties with a lot of farms, at least 600, and counties with fewer than 600. You can see that our random sample just happened to give us 129 counties in that first group and 171 in the second. The table then shows the average acreage and the standard deviation, calculated just within each of those two groups.
And here we see the formulas in action. Let's look at that top calculation for the standard error of the mean. That's our simplified large sample formula. You can see the finite population correction up front, then inside the square root, we take the standard deviation from the table, that 258,249, square it to get the variance, and divide by our domain sample size, 129. That gives us a standard error of about 21,553. Now contrast that with the bottom section. Here we're estimating the total acreage and we're assuming we don't know the domain size. That's our scenario 2 method. The standard error calculation here uses the total population size n and the standard deviation of our special U variable, which was calculated across the whole sample of 300. This really shows how the formula you use depends entirely on what you know about the population.
And of course, this isn't just for farming. The source material also looks at a survey of boat owners. In that case, the domain is any household with a motorboat over 16 feet long. We can use the exact same methods to estimate the average number of kids in those households. And if we don't know the total number of these households in the whole state, we can use that n times u bar method to estimate the total number of kids living in them. It's an incredibly flexible technique.
Okay, so let's pull back for a second and just summarize why we go through all this effort. Why is this technique so important? Why does it matter so much to get these estimates for subgroups?
All right, here are the key things to remember. First and foremost, the big challenge is that our domain sample size, n sub d, is a random variable. That's the problem we had to solve. Second, the brilliant solution is to reframe the whole thing as a ratio estimation problem. That gives us the right mathematical tools. Third, the method is really flexible. It adapts depending on whether or not we know the actual size of our domain in the population. And finally, when you put it all together, mastering this technique is what lets us go beyond those simple, sometimes misleading population averages and get a much, much richer story about the specific groups that make up our world.
You know, understanding how these numbers get made is incredibly powerful. It helps you be a much smarter consumer of the data you see every single day. So the next time you see a stat about the opinions of rural voters or the habits of Gen Z, you'll actually understand the machinery working behind the scenes. And that leads me to my final question for you. Now that you know how this is done, what subgroups in the world around you do you think deserve a closer look?